Welcome. Tonight there is nothing you need to do but rest. Let your breathing slow. Let your shoulders release their weight. Let your mind drift outward toward the stars. The observable universe, right now, stretches 93 billion light-years across. That number describes not a place we could ever travel, but the farthest reach of light that has had time to reach us since the beginning. Beyond that edge, space continues, unseen, folded into a darkness too distant for any signal to have crossed yet. You are here, small and warm, inside all of it. 13.8 billion years is how long light from the cosmic microwave background has traveled to reach us. This faint afterglow fills the entire sky, a whisper left over from the universe's early heat. It arrives from every direction at once, unchanged since matter first became transparent to light. The light entering telescopes tonight began its journey before any star we now see was born. It carries no image, only warmth, spread thin across billions of years of silence. Human eyes can only perceive a narrow slice of the electromagnetic spectrum. Radio waves, X-rays, gamma rays, and infrared light all move through the room around you right now, utterly invisible. What we call color is only a thin band, a keyhole view onto a much larger reality. Bees see ultraviolet patterns on petals. Snakes sense the heat of a body in darkness. The universe hums in wavelengths our bodies were never built to notice. The fastest spacecraft ever built would take 80,000 years to reach the nearest star. Even traveling at tens of thousands of kilometers per hour, the distance between stars swallows that speed whole. Proxima Centauri sits just over 4 light-years away, close by cosmic standards, and still nearly unreachable. A journey begun by the builders of the pyramids would only now be arriving. Out there, distance is measured less in miles than in centuries. Voyager 1 has only just left the heliosphere after 46 years of flight. Launched in 1977, it now drifts through interstellar space, carrying a golden record of Earth's sounds and voices. Its radio signal, moving at the speed of light, takes over 20 hours to reach mission control. It is the farthest human-made object from home, still humming faintly, still listening back toward a sun that now looks like just another star. Peering through the James Webb Space Telescope, astronomers can see galaxies as they appeared 13.4 billion years ago. That light left its source when the universe was only a few 100 million years old, long before the Sun or Earth existed. Webb does not look into the past the way memory does. It simply receives old light, still arriving, still true. Each image is a fossil made of photons. No human has lived longer than about 122 years. Jean Calment, born in Arles in 1875, held that record until her death in 1997. Her lifetime spanned the invention of the automobile and the first steps on the moon. Even so, against the timescales of stars and galaxies, a human life passes like a single breath, barely long enough to notice the sky has moved at all. Civilization as we know it is only about 12,000 years old. Agriculture, cities, writing, and calendars all emerged after the last ice age loosened its grip on the Earth. Measured against the universe's 13 billion-year history, all of human history fits inside a sliver too thin to see on a cosmic timeline. Everything we have built, every language ever spoken, belongs to this brief, bright moment. Earth's magnetic field has flipped hundreds of times across 4.5 billion years. North becomes south, then south becomes north again, over spans of hundreds of thousands of years. The field never fully vanishes during these reversals. Though it weakens and grows strange, its lines tangled instead of simple. Compasses from 100,000 years ago would have pointed the opposite way. The planet has always been quietly rearranging itself beneath our feet. The Sun is about halfway through its 10 billion-year hydrogen-burning lifetime. For roughly 4.6 billion years, it has fused hydrogen into helium at its core, releasing the light that now warms this room. It has enough fuel remaining for about 5 billion more years of steady burning. Long after every human alive tonight is gone, the Sun will still rise, patient and unchanged, exactly as it does this evening. Let your breath find its own slow rhythm now, no need to guide it. Notice the pause after each exhale, the small stillness before the next breath begins. With every out-breath, let your shoulders drop a little further into the mattress. The air moves in, unhurried, and moves out again, longer this time, like a tide easing back from shore. Nothing more is required of you than this one breath, and then the next. Every billion years, the Sun grows brighter by about 10%, its core gradually compacting as helium accumulates within. This brightening is a natural part of stellar aging, not a flaw in its fusion. A billion years from now, Earth will receive noticeably more warmth than it does tonight. The change is imperceptible within any single lifetime, yet inevitable across deep time, reshaping the climate of every world in its light. In about 1 billion years, Earth's oceans are expected to boil away entirely. As the Sun's output climbs, the planet's surface temperature will rise past the point liquid water can survive. Rivers will vanish first, then lakes, and finally the vast seas themselves will lift into the atmosphere as vapor. What remains will be a dry, cracked world, its blue color faded from memory. The Earth we know depends entirely on this narrow, fragile balance of warmth. Photosynthesis will become impossible in roughly 1 billion years, as rising temperatures pull carbon dioxide out of the atmosphere. Weathering rocks absorb the gas faster under a hotter sun, starving plants of what they need to build sugars from sunlight. Forests will thin, then fields, then the last hardy mosses clinging to shaded stone. Without this ancient chemical exchange, the very foundation of Earth's food chains will quietly unravel. Andromeda, our nearest large neighboring galaxy, is moving toward us at about 110 kilometers per second. Even at that tremendous speed, it remains too distant to see the approach with the naked eye. On a clear night, it appears only as a faint smudge of light, 2.5 million years old by the time it reaches your eyes. Every year, the gap between our two galaxies grows a little smaller. About 4 billion years from now, the Milky Way and Andromeda will begin to merge. Their outer stars will drift into new patterns, pulled gently by each galaxy's gravity. The night sky, if anyone remained to watch it, would slowly fill with a second river of stars stretching overhead. This process will unfold across hundreds of millions of years, far too gradual for any single generation to notice. Even as two galaxies merge, their stars almost never collide. Space within a galaxy is so vast that stars pass each other like ships crossing an ocean at night, each unaware of the other's presence. The average distance between neighboring stars measures in trillions of kilometers, dwarfing the stars themselves. Astronomers expect the Milky Way and Andromeda to pass through one another with barely a single direct impact between their countless suns. Astronomers have already given this future merged galaxy a name, Milkomeda. The word blends both galaxies into one, much as their stars and gas will someday blend into a single elliptical structure. Milkomeda will likely lose the elegant spiral arms both galaxies wear today, settling instead into a smoother, rounder shape. It will glow steadily for trillions of years afterward, a single vast home for whatever remains to call it that. 5 billion years from now, the Sun will swell into a red giant. Its outer layers will expand far beyond their current reach, turning the sky overhead a deep, smoldering red. The Sun's diameter could grow large enough to swallow the orbit where Earth circles today. Its light will dim in color but grow enormous in size, radiating heat across a solar system utterly transformed from the one we know tonight. Mercury and Venus, the two innermost planets, will likely be swallowed whole. As the Sun's outer atmosphere reaches outward, their rocky surfaces will melt, then vaporize, then vanish entirely into the star that once warmed them. Billions of years of steady orbits will end within a span of mere millions, a blink by comparison. Their disappearance will mark the first casualties of the Sun's long final act. Earth's fate during the Sun's red giant phase remains uncertain. Some models suggest our planet's orbit will drift outward as the Sun loses mass, sparing it from being swallowed. Other calculations show tidal drag pulling Earth inward into the swollen star's outer atmosphere. Astronomy has not yet settled which outcome wins. Either way, the oceans will have boiled away long before the question is decided. Weight settles into the mattress beneath you now. Your feet grow heavy first, sinking deeper with each breath. That heaviness rises through your ankles, your knees, resting into your legs like sand settling at the bottom of a jar. Your hips ease into the bed, then your lower back, releasing whatever it carried today. Shoulders drop, arms grow loose, hands unclenching on the sheets. Even your jaw can rest now, heavy and still. Shedding its outer layers, the Sun will scatter itself across space in the shape of a glowing planetary nebula. Streams of gas drift outward in delicate shells, lit from within by the exposed stellar core. For a brief cosmic instant, mere thousands of years, this nebula will glow in vivid color, rivaling the beauty of nebulae photographed across the galaxy tonight. In time, the light fades as the gas thins, dispersing into the emptiness between stars. Left behind is the naked core, no longer able to fuse light elements, collapsing into a white dwarf no larger than Earth itself. This is what remains after the outer layers drift away as nebula, a stellar ember, dense and small, still shining but generating no new heat. All of that mass, once spread wide across a giant star, packs itself into a sphere you could cross in a matter of weeks. Quantum mechanics, not fusion, holds a white dwarf up against its own gravity. Electrons packed so tightly resist being squeezed any further, a phenomenon physicists call degeneracy pressure. This strange support has nothing to do with heat or burning. It exists because two electrons cannot occupy the same quantum state. Without it, gravity would crush the star down to something smaller still. Cooling from a white dwarf into a cold, dark ember will take more than 1 trillion years. Even without new fuel, the star releases its leftover heat at a barely perceptible pace. Long after every other process in the galaxy has quieted, these embers will still glow faintly, dim red beacons fading toward black. Astronomers call this final stage a black dwarf. Though none exist yet, the cosmos simply is not old enough. Inside our own galaxy, the pace of star birth is already slowing down. Clouds of hydrogen gas that once fed generation after generation of stars are thinning with each passing era. Fewer stellar nurseries glow among the spiral arms than in the galaxy's youth, billions of years ago. The Milky Way is not dying, but it is aging, running low on the raw material of creation. 10 billion years ago, the universe burned brighter than it ever will again. Cosmologists call this the peak of star formation, a golden age when galaxies churned out new suns at many times today's rate. Vast clouds of primordial gas collapsed rapidly, seeding the cosmos with light. Every star born since has arrived after this crescendo, in a universe already past its brightest hour. Roughly 10% of all the stars the universe will ever create have yet to ignite. Despite a history already stretching across billions of years, most of the cosmos's stellar story lies ahead rather than behind. Unlit clouds of gas still linger in galaxies, waiting across eons for gravity to pull them into new suns. The night sky, in some sense, has barely begun. Something invisible is pushing the universe apart faster, with every passing year. Physicists call it dark energy, a mysterious pressure filling empty space itself. Unlike gravity, which pulls matter together, this force pushes galaxies apart, and its effect grows stronger as space stretches wider. It remains one of the least understood quantities in all of physics, known mainly by the expansion it causes. Edwin Hubble discovered in the 1920s that galaxies race away from us in every direction. The farther a galaxy sits, the faster it appears to recede, a relationship now called the Hubble constant. This single number tells cosmologists how quickly space itself is stretching at any given era. Measuring it precisely remains one of the most debated pursuits in modern astronomy, refined again with each new instrument that gathers older, fainter light. Beyond a boundary called the Hubble sphere, galaxies are already moving away faster than light itself can travel. This breaks no law of physics, since space is doing the stretching, not the galaxies moving through it. Those galaxies still exist, shining somewhere beyond our reach, but their light will never again cross the widening distance to us. Some of what we glimpsed tonight has already slipped past that unseen edge. Somewhere beyond these walls, a low hum rises and fades, a furnace, distant traffic, an old house settling into night. Let it arrive, and let it pass without needing to name it. Your breath can follow that same rhythm, rising, holding, releasing, asking nothing more of you than to continue. Each sound that comes and goes is proof that the world keeps turning on its own, without your help. You may rest inside that turning, unattended, already safe. 100 billion years from now, the night sky will have emptied of nearly everything we recognize today. Every galaxy beyond our own merged cluster will have crossed beyond the reach of light, carried off by the ever-widening gulf of space. Only the stars of our combined local group will remain visible, drifting together in otherwise blank darkness. The rest of the universe will simply vanish from view, though it will still be there. The oldest light in the universe, the cosmic microwave background, will eventually stretch beyond any instrument's ability to detect it. As space keeps expanding, this faint afterglow of creation grows dimmer and redder with every passing age. Future astronomers, however advanced their tools, will find only silence where this ancient signal once hummed. The evidence of the universe's fiery beginning will fade first from view, long before the stars themselves go dark. Triangulum, a modest spiral galaxy, some 3 million light-years away, may eventually be drawn into the merger of the Milky Way and Andromeda. Its gravity already feels the pull of its two larger neighbors, tracing a slow orbit around their combined mass. Across billions of years, this third galaxy could spiral inward and join the growing structure taking shape at the heart of our local group. 3 separate island universes would then become one. No trace of the Big Bang may remain for civilizations arising in the far future. Once the cosmic microwave background fades beyond detection and distant galaxies vanish past the horizon, the sky will offer no evidence the universe began in a single hot moment. Astronomers born into that era might reasonably conclude their galaxy was simply eternal, alone, unchanging. The story of creation could become unreadable, erased not by destruction but by distance. Red dwarf stars, small and dim compared to the Sun, burn their hydrogen fuel with remarkable patience. The lightest among them sip fuel so slowly that they could keep shining for trillions of years, far outlasting stars like our own. Unlike the Sun, these faint stars mix their fuel evenly through convection, drawing on their entire reserve rather than wasting most of it in an unused core. They are, in their own way, the universe's most enduring stars. 10 trillion years from now, the smallest red dwarfs may still be steadily fusing hydrogen in their cores. This stretch of time dwarfs the current age of the universe many times over. Long after the Sun has cooled into a dark ember, These modest stars will continue their slow burn, faint red points scattered across an otherwise darkening cosmos. They represent, perhaps, the last stubborn glow of stellar fusion in an aging universe. Star formation across the entire universe will effectively come to an end around 100 trillion years from now. The vast reservoirs of hydrogen gas that once fueled new suns will finally be exhausted, spent by galaxy after galaxy of stellar birth. No new stars will ignite after this point, only the slow fading of those already burning. The universe will have used up its capacity for creation, entering an age defined by ending rather than beginning. This great expanse of future time already carries a name among cosmologists, the degenerate era. It opens once ordinary starlight fades, stretching across a length of time that makes today's universe look like its earliest infancy. White dwarfs, neutron stars, and black holes will dominate the cosmos, held together not by fusion but by degeneracy pressure, a strange quantum resistance to further collapse. The name marks endurance, a long, dim age of remnants rather than birth. 1 quadrillion years from now marks the true end of conventional starlight. Even the most patient red suns, having sipped their hydrogen through slow convection, will finally exhaust every trace of fuel. Their fusion fires will gutter and go dark, leaving dense embers of degenerate matter behind. After this point, no star anywhere in the universe will shine through nuclear fusion the way stars do tonight. Brown dwarfs, the failed stars too small to ignite full fusion, still hold a slow spark of activity long after true stars go dark. Across immense stretches of time, they fuse traces of deuterium, a heavier form of hydrogen, releasing only the smallest breath of energy. A single brown dwarf might glow this way for quadrillions of years. Eventually, even this last ember cools, and the sphere turns dark and inert, drifting alone. Let a low heat begin somewhere near your feet, the kind that rises from thick socks on a cold night. Let it climb into your ankles, unhurried, then your calves, then the backs of your knees. Feel it move into your thighs, heavy and slow, then rest through your hips and lower back. Let it rise through your chest, your shoulders, down each arm to your fingertips, until your whole body carries this low, drowsy heat, and your eyelids grow too heavy to lift. Stellar remnants will vastly outnumber active stars in the far future. White dwarfs, neutron stars, and stray black holes will make up the overwhelming majority of stellar objects, while only the last red dwarfs continue their long, dim burn. For every star still shining, thousands more will exist only as cooling embers or gravitational shadows. The universe's population of stars will have shifted from living furnaces to quiet, dark relics. Planetary orbits will slowly decay across immense stretches of time, drawn inward by gravitational radiation. Two orbiting bodies constantly emit ripples in space-time, losing a minuscule amount of orbital energy with every pass. Over spans far longer than the current age of the universe, this trickle adds up, drawing planets closer to their stars. The process is imperceptibly small today, yet given enough eons, orbits can collapse entirely. Close stellar encounters will eventually eject most planets from their systems. As galaxies empty and stars drift among sparse remnants, gravitational tugs from passing bodies grow more significant over time. A single near pass can be enough to fling a planet free of its star's pull entirely. Across the vast future, these rare encounters accumulate, and most worlds will end up wandering alone through open space. Nearly 90% of all stars will be flung out of their home galaxies within 10 quintillion years. Countless gravitational encounters, accumulated over unimaginable stretches of time, slowly loosen every star's bond to its galactic home. One by one, Stars drift free, cast into the vast spaces between galaxies. What once were bright, structured spirals will empty out, leaving only a sparse remainder gravitationally intact. The remaining stellar remnants, those not flung outward, will spiral slowly toward their galaxy's center. Gravitational interactions rob these leftover stars of orbital energy over immense timescales, drawing them inevitably inward. In time, most surviving remnants will fall into the supermassive black hole that once anchored their galaxy's core. What began as a luminous galaxy will end as a single, swollen point of gravity. Galaxies, as gravitationally bound structures, will dissolve within about 100 quintillion years. Stripped of most of their stars through ejection and inward collapse, galaxies will lose the coherence that once defined them. What remains will be sparse and diffuse, no longer resembling the bright spirals and ellipticals of tonight's sky. The very concept of a galaxy, as a bound island of stars, will cease to hold meaning. Deep inside a neutron star, a force called neutron degeneracy pressure holds back the crushing pull of gravity. Packed to the density of an atomic nucleus, neutrons resist being pressed any closer together. This quantum resistance is what keeps the star from folding into a black hole. A neutron star crams the mass of our Sun into a sphere, no wider than a city, and this pressure alone keeps that sphere from collapsing further. When two neutron stars spiral together and finally collide, the resulting collision can forge gold and other heavy elements. Under those extreme conditions, atomic nuclei are crushed and fused in ways no ordinary star could manage. Astronomers have watched this happen directly, catching both light and gravitational waves from such a merger. Much of the gold in your jewelry, if you wear any, may trace its origin to an event exactly like this. Proton decay, if it occurs, would dissolve all ordinary matter over spans of time beyond comprehension. Protons form the foundation of every atom, every rock, every star we see. If they are not perfectly stable, everything built from them would break apart, piece by piece. This process, should it happen at all, works on a timescale no human observation could ever confirm. 10 to the power of 34 years, that is, the lower bound experiments have set for the proton's lifetime. Enormous underground detectors, shielded from cosmic rays, have watched tanks of pure water for any hint of proton breakdown. So far, not a single decay has ever been confirmed. That silence itself tells physicists something remarkable. Protons, if they decay at all, do so unbelievably rarely. Let your attention rest on something small, dust suspended in a beam of window light, barely moving, held in place by nothing but stillness. Notice how little effort it takes to simply hang there weightless, needing nowhere else to be. Your body can borrow that same ease now, unclenching fold by fold, breath after breath. Nothing is required of you tonight except this drifting, unhurried stillness. White dwarfs and neutron stars, should protons decay, would gradually evaporate away, piece by piece, across ages far longer than any that preceded them. Every atom locked inside these stellar remnants carries the same fragile chance of dissolving. Over such vast stretches of time, even the densest matter in the universe would thin into almost nothing. What once were stars would become little more than a memory of structure. Turning matter into light is, in effect, what proton decay would accomplish, converting stellar remnants into positrons, electrons, and radiation. Every particle inside a star's collapsed core carries this same fate, waiting across immense stretches of time. Freed positrons and electrons may eventually meet and annihilate, releasing yet more radiation into the dark. What began as dense matter would end as something closer to pure light drifting through space. Iron stars, purely hypothetical, could form once every process of fusion and decay has run its course. If protons truly decay and stars burn through every fuel available to them, whatever remains would condense into the most stable element there is, iron. Given enough time, ordinary matter might rearrange itself into these dim, dense spheres. No iron star has ever been observed, and none may ever need to be, given how distant this era lies. A number with 1,500 zeros after it, written out in years, roughly names the span quantum tunneling might need to fuse ordinary matter into iron. At that scale, even resting atoms behave like restless travelers, occasionally passing through barriers that ordinary physics says they should never cross. Across such stretches, cold matter might still rearrange itself, one rare tunneling event at a time. Nothing alive could ever wait long enough to witness it, yet mathematically, the possibility remains open. Collapsing under the gradual push of quantum tunneling, these iron stars would eventually become black holes. Once enough of their matter has rearranged into iron, the star's own gravity finds a new way forward, since fusion can no longer hold the structure up. A rare tunneling event nudges the star past its tipping point, and collapse follows. What was once the final stable form of matter becomes, in the end, a black hole once more. Massive stars, having burned through every form of fuel available to them, can no longer hold themselves up against their own gravity. Their cores collapse inward, compressing matter into a point denser than anything else known to physics. What remains is a black hole, a region so warped that even light bends helplessly around it. This collapse has likely happened billions of times across cosmic history, each one silent, each one unseen from Earth. The event horizon marks the boundary from which nothing, not even light, can ever return. Crossing it is not something you would feel. No wall, no resistance, just a point past which the universe no longer answers back. From outside, the horizon looks like a sphere of utter dark, sharply outlined against the stars. Nothing that crosses that line, not light, not matter, not information, finds a way out again. Stephen Hawking, in the 1970s, predicted that black holes are not entirely black. Working through the mathematics of quantum fields near a collapsed star, he found that black holes should emit particles and lose mass over time. This idea, radical when it appeared, reshaped how physicists think about gravity and information together. Given enough time, Hawking's calculations suggest, even the darkest object in the universe fades. Hawking radiation seems to arise from quantum effects occurring right at the edge of a black hole's horizon. Empty space is never truly empty. Particle pairs flicker briefly into existence and vanish again everywhere, even here, near a horizon. One particle of such a pair can fall inward while its partner escapes outward as radiation. Over immense stretches of time, this leak is thought to carry the black hole's mass away with it. Smaller black holes, oddly, evaporate faster than their far larger relatives. A black hole's temperature rises as its mass shrinks, so the smallest ones radiate more intensely near the end of their lives. A black hole. The mass of a mountain might evaporate in a fraction of a second. One the mass of a star or a galaxy's core needs a span of time barely expressible in ordinary numbers. Behind closed eyes, there is only a wide, unlit hush, nothing to look at, nothing to look for. The jaw loosens, top and bottom teeth easing apart by the smallest measure. Small muscles around the eyes, tired from a full day of focusing, finally let go their grip. The forehead widens, smooths, no longer holding any expression at all. Whatever remains of tonight's thoughts can rest there now, unfinished, needing nothing more from you. Roughly a 1 followed by 67 zeros marks how many years a black hole with the sun's mass would need to evaporate completely. Numbers this size lose any real meaning, standing in more as a symbol for near eternity than a countable span. Long before that clock runs out, every star, planet, and scrap of ordinary matter will have changed form many times over. Even patience, on this scale, becomes a kind of abstraction. A supermassive black hole, the kind sitting at a galaxy's center, could take up to a 1 followed by 100 zeros years to evaporate. Such black holes hold the mass of millions or billions of stars, so their radiation leaks out at an almost immeasurably slow rate. Long after every star has died and every remnant has cooled, these giants would still remain, holding on to their mass. Their eventual fading marks one of the last events in any timeline of the universe. The largest black holes yet found exceed 60 billion times the mass of the Sun. Discovered at the centers of enormous galaxies, these objects are so vast that light takes days to cross their shadows alone. Their gravity has shaped the galaxies around them for billions of years, guiding the orbits of stars far beyond ordinary sight. Even among giants, these black holes stand as some of the most extreme objects physics has ever measured. In its last instant, evaporation ends with a burst of high-energy radiation. As a black hole's mass dwindles toward nothing, its temperature climbs sharply, and its final moments release energy far faster than anything that came before. This closing flash, brief compared to the eons preceding it, marks the true end of the black hole's existence. After that release, nothing remains but the radiation still traveling outward into empty space. Once every black hole finishes evaporating, only a thin mist of particles remains, scattered across the space they once filled. Photons, electrons, neutrinos, and their antiparticles move apart at ever greater distances, no longer held by gravity strong enough to gather them again. No stars will ignite from this material. It is too dilute, spread across a volume that dwarfs anything that came before it. What remains is not true emptiness, but something remarkably close to it. Cosmologists have given this stretch of time its own name, the Black Hole Era. It marks the long chapter when black holes, from stellar remnants to galactic giants, stood as the universe's dominant structures, radiating themselves away in slender threads of energy. Before this era, stars and galaxies filled the sky. After it, only their gravitational remains stayed behind, dissolving into light over spans beyond ordinary counting. The name captures both the era's length and its hush. The information paradox sits at the center of black hole physics, asking whether anything that falls in is ever truly lost. Everything a black hole swallows, in principle, carries information, the exact arrangement of atoms, memories, and matter. Classical physics said that information vanished forever behind the event horizon. Quantum theory insists it cannot, since information is never supposed to disappear from the universe entirely. The disagreement between these two ideas has occupied theoretical physicists since the 1970s. Most physicists now lean toward the idea that information survives, encoded subtly within the pattern of Hawking radiation itself, rather than escaping in one dramatic flash. Details about what fell in seem to leak out gradually, hidden in tiny correlations between particles emitted over the black hole's long lifetime. Stephen Hawking himself came to accept this view before his death. The paradox is not fully resolved, but the balance of evidence now favors preservation over loss. After the last black hole fades, the universe enters what cosmologists call the Dark Era. No stars burn, no black holes remain, and no light source of any kind will switch on again. Only a low hum of ancient particles, spread almost infinitely thin, marks that anything exists at all. This period is expected to last far longer than every era before it combined. It is less a place than a condition, an unbroken dimness stretching without end. Within this dark era, The universe's contents narrow to just a few kinds of particle. Photons stretch toward enormous wavelengths, neutrinos pass through everything without effort, and light leptons such as electrons and positrons scatter across unimaginable distances. No structure of any size holds together anymore. What remains is a thin, cold soup of particles, moving through a universe that has grown vastly larger than any galaxy that ever existed within it. Notice your breath without trying to change it. Let it come in and let it go, a touch longer on the way out each time. There's no place this breath needs to reach. It simply empties, making room for the next to arrive on its own. Let your shoulders follow that same release, settling further with every exhale. Just breath, arriving and leaving, until the mind grows still enough to rest. Positrons and electrons, the last scraps of ordinary matter, may eventually meet and annihilate into pure radiation. Each collision converts mass entirely into energy, releasing a burst of light with no particle left behind. Over the near-endless span of the dark era, these encounters grow rarer and rarer, separated by stretches of time too long to picture. Eventually, matter as we understand it may cease to exist in any form. Only photons will carry forward the energy that once made up atoms. Entropy, the measure of disorder within a system, continues climbing toward its highest possible value throughout these eras. Each transformation, from star formation to black hole evaporation, nudges the universe further from order and further from usable structure. Physicists describe this climb as a one-way process, never reversing course on its own. As entropy approaches its ceiling, the distinctions between past and future, between hot and cold, begin to fade entirely. Very little will be left to tell one moment from the next. The second law of thermodynamics stands behind all of this. Entropy in a closed system never decreases on its own. Heat flows from hot to cold, never the reverse, and order gives way to disorder given enough time. This law has held in every laboratory test and every astronomical observation ever made. Applied to the universe as a whole, it points in one direction only, a long exhale toward equilibrium, from the fires of early stars to the dim, uniform stillness of a far, far future. Maximum entropy marks the theoretical endpoint cosmologists call heat death. At this stage, disorder reaches its highest possible value, and no structure remains to change. Every star has burned away, every black hole has evaporated, every particle floats alone in the dark. There is no more work left to do, no imbalance left to level. The universe rests evenly at one final temperature, a stillness with nothing left to become. In heat death, no usable energy gradients remain to do work. Energy still exists, spread evenly through space, but nothing can flow from hot to cold anymore. Without that flow, no engine can turn, no reaction can spark, no light can shine anew. It is not an absence of energy, but an absence of difference. Difference, it turns out, is what allows anything at all to happen. Temperature differences across the universe will approach absolute uniformity. Hot embers near dying stars and cold, empty pockets of space will edge closer to the very same value. Given enough time, no thermometer could tell one place from another, or one moment from the next. Warmth itself becomes indistinguishable from cold. The whole of space will hold one faint, shared temperature, unbroken across distances beyond imagining. Cosmic expansion will stretch all remaining particles far beyond causal contact. Space itself keeps widening, carrying each particle farther from every other. Eventually, the gaps grow so vast that no signal, not even light, could cross them in any span of time. Each particle becomes an island, unreachable by any other point in the cosmos. Cause and effect. The thread linking one event to another simply runs out of room. The observable universe will one day contain only a single fundamental particle, expansion will have carried every other particle beyond the horizon of what any one point could ever detect. A lone photon, or perhaps a lone electron, would mark the entire visible cosmos from wherever it happened to sit. There would be no neighbor left to measure against, no second point of reference. Space would stretch around it, like an ocean, around one floating grain of sand. Cosmologists debate whether heat death truly marks the universe's ultimate fate. The scenario follows naturally from known physics, assuming expansion continues just as it appears to today. But the equations describing dark energy carry uncertainties that widen across such deep time. Small differences in those numbers, invisible to any instrument now, could send the story down a very different path. Nothing about the far future is quite as settled as it may sound. An alternative fate, known as the Big Rip, would tear apart atoms themselves. In this scenario, the force driving cosmic expansion keeps strengthening rather than staying constant. Galaxies would separate first, then stars, then planets, and finally the very nuclei holding matter together. Rather than fading into uniform stillness, the universe would end in a final, silent unraveling. Every bond, from gravity to the strong nuclear force, would lose its grip at once. Feel the weight of your body now, resting fully into whatever holds it. Let your feet grow heavy first, sinking into the mattress like stones, settling into warm sand. Let that heaviness climb upward, through your legs, your hips, your lower back, each part giving its weight away. Your arms follow, heavy at your sides, fingers loose and unconcerned with holding anything at all. Even your head grows heavy against the pillow, the whole body sinking, one part at a time, into rest. The Big Rip depends on dark energy's density increasing rather than staying fixed. If the repulsive force behind cosmic expansion grows stronger as the universe ages, it would eventually overpower gravity, even at the smallest scales. Atoms hold together today because their internal forces still outmatch the pull of expanding space. Should that balance tip the other way, no structure, however small, could resist being pulled apart. Current data slightly favor a stable cosmological constant over any runaway version of dark energy. Measurements from distant supernovae and the cosmic microwave background align most closely with a constant value, unchanged through cosmic history. That evidence leans away from the Big Rip, at least for now. The margins of uncertainty remain wide enough, though, that a gradually strengthening dark energy field cannot yet be ruled out. The universe's final chapter still waits on better instruments and longer study. A different ending, known as the Big Crunch, would require the universe's expansion to reverse. Gravity, in this scenario, wins out over the force pushing space apart, pulling every galaxy back toward the others. The vast distances that once separated all things would begin to shrink, slowly at first, then with gathering speed. Stars would crowd closer, temperatures would climb, and the sky itself would begin to glow. It offers a mirror image of the Big Bang, only running in reverse. Before 1998, most cosmologists leaned toward the crunch as the universe's likely fate. Gravity was assumed to be the deciding force, strong enough eventually to halt and reverse the expansion begun at the Big Bang. That assumption held until new observations arrived. Observations that would upend decades of quiet consensus. The universe, it turned out, was not slowing down at all. It was speeding up, and no one had expected that. Two research teams, studying a class of exploding stars called Type 1 supernovae, made a striking discovery in the late 90s. These stars burn with a reliable, calibrated brightness, letting astronomers use them as distance markers across billions of light years. Distant supernovae appeared fainter, and therefore farther away than a steadily expanding universe would predict. The only explanation that fit was that expansion itself was accelerating. space was pushing outward faster with each passing age. The Nobel Prize in Physics for 2011 honored this discovery of cosmic acceleration. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the recognition for revealing that the universe's expansion was speeding up rather than slowing down. Their work rested on years of patient supernova surveys, comparing brightness against distance across cosmic history. The finding reshaped cosmology's central question, from asking when expansion would end to asking why it never seems to stop growing. Vacuum decay describes a hypothetical event where a truer, lower-energy vacuum state emerges from within our own. Physics treats empty space not as pure nothingness, but as a field with its own underlying energy, one that may not yet rest at its lowest possible value. If a small region were to shift into that deeper state, the very laws governing particles and forces there would change. It would be a transformation of reality's rules, not merely of matter. Such a bubble, if it ever formed, would expand outward at the speed of light. Nothing could outrun its edge or send warning ahead of its arrival. Inside that boundary, the constants that shape atoms, forces, and chemistry would shift to new values, unrecognizable to anything built under today's physics. Matter as we know it would simply cease to hold its familiar form. The boundary itself would arrive and pass in the same silent instant. Physicists estimate that the Higgs field, the very field giving particles their mass, may rest in a metastable rather than a fully stable state. A metastable vacuum sits in a shallow valley of energy, stable enough for now, but not at the deepest possible point. Calculations suggest a true lowest state may exist somewhere beyond it, separated by an energy barrier. The universe, by this reasoning, may simply be sitting comfortably in a valley that is not the very bottom. If vacuum decay is real, it could begin anywhere without any warning at all. No signal would precede it, no gradual change would hint at its approach. It might start in the heart of a distant galaxy, or in the space beside your own window, chosen by pure quantum chance rather than any visible cause. Whatever triggers it, the event itself would announce nothing beforehand, arriving already complete. Somewhere beyond the room, a low hum rises and fades, the kind of sound a house makes late at night, when everyone inside has stopped moving. It could be wind finding a gap beneath a door, or a pipe settling as the air grows cooler. Let it come, and let it go without following it anywhere. Your breathing can match its rhythm, rising, pausing, falling away again. Nothing needs your attention now, only this slow tide of sound, arriving, receding, fainter each time, further away. Some calculations suggest the vacuum could remain stable for 10 to the 100th power years or more, a span so vast that all the ages already described would vanish inside it like a single grain of sand. Even black holes, even the slow fading of protons, would complete their entire span long before this deeper question resolves itself. Whether that stability truly holds is still unknown. It remains one of the longest waits physics has ever imagined. No observer could ever expect to witness vacuum decay directly, not even across an entire lifetime spent watching the sky. The event, if it happens, would complete itself faster than any nervous system could register a change. Light itself could not outrun the transition, so no warning, no glimpse, no final thought would come before it. For any single observer, the odds of consciously catching such a moment are effectively zero. Cosmic inflation theory suggests our own universe began inside a state much like the false vacuum now imagined for its ending, a bubble of unstable energy that expanded outward with tremendous force. In this picture, the same instability that might one day close everything is the instability that once opened it. Beginnings and endings, seen this way, share a common physical grammar. The universe, some cosmologists suggest, was born from a decay resembling the one it may someday undergo. Some models propose that vacuum decay would not only end things, but start them again elsewhere. Inside the expanding bubble, physical constants might settle into wholly different values from our own. Such a region could become its own separate pocket universe, unreachable and unaware of what came before it. In some versions of the mathematics, one ending becomes another universe's quiet beginning. Multiverse theories picture infinite universes stretching outward, each shaped by its own set of physical constants. In some, gravity might pull harder or weaker. In others, light itself might carry different properties entirely unlike our own. Most of these hypothetical realms, if they exist at all, would remain forever cut off from ours, unreachable by any signal or observation. The idea stands as a mathematical possibility rather than a confirmed feature of nature. Henri Poincaré's recurrence theorem, written more than a century ago, suggests that any bounded system will eventually return to a state resembling where it began. Applied to the universe as a whole, this would mean that given enough time, particles could reassemble into patterns echoing today's arrangement. The theorem promises resemblance, not exact repetition. Whether it truly applies to the whole cosmos remains an open mathematical question. A number almost impossible to write down describes how long full cosmic recurrence might take. Estimates place it near 10, raised to the power of 10, raised again to the power of 10, raised finally to the 76th power. Ordinary comparisons fail at this scale. Nothing in experience offers a fair measure against it. It functions less as a prediction than as a way of gesturing toward depth of time beyond comprehension. Boltzmann brains are a curious hypothetical, fully self-aware minds arising suddenly from random quantum fluctuations, without any body, history, or surrounding universe. Such a mind would flicker into being complete with a single false memory of a life it never lived. Then, just as quickly, it would dissolve back into the disorder it came from. The idea remains a thought experiment, useful mainly for testing the outer limits of probability. In a universe old enough and lasting long enough, Boltzmann brains might vastly outnumber minds that arose through ordinary evolution. Random fluctuations, however rare, would have endless time to occur, while evolved observers require narrow and specific conditions to exist at all. Across near infinite time, rarity multiplied by patience can overtake rarity born of complexity. The comparison unsettles more corners of cosmology than it comforts. A growing number of physicists argue that if Boltzmann brains truly outnumber evolved minds in the far future, something in our present models must be incomplete. A universe predicting more random flickers of consciousness than real observers seems to undercut its own logical foundation. This tension, sometimes called the Boltzmann brain problem, remains unresolved within cosmology. It is treated less as a threat than as a clue pointing toward a deeper theory. Let a warmth begin now, low in your chest, and rest there a moment before it spreads. Let it move down through your arms, reaching each finger with a slow, heavy glow. Let it pool in your stomach, then drift lower still, into your hips, your knees, the long bones of your legs. Let it rest finally in your feet, warm and unmoving, while the rest of you grows just as still. There is only this warmth now, spreading at its own unhurried pace, asking nothing of you but to let it continue. A true vacuum, stripped of every particle and field, never truly goes silent. Quantum uncertainty allows fluctuations to conjure pairs of particles from what should be nothingness. They flicker into being, borrowing energy the universe seems to permit only in secret. Before that debt can be noticed, they vanish again. This is not disorder. It is the arithmetic underlying empty space itself, running quietly beneath every star and every void alike. Throughout the space between galaxies, this flickering never stops. Virtual particle pairs, matter paired with its opposite, appear and disappear countless times within a single second, everywhere at once. They exist too briefly to be caught by any instrument, yet their subtle effects ripple through measurable physics, bending the paths of light and shifting atomic energy levels by fractions no larger than a whisper. Even the darkest reach of space hums with this activity. Long after heat death drains the universe of usable energy, the quantum fabric underneath may not fall completely silent. Fluctuations could still occur, spaced further and further apart as expansion stretches even the fabric of chance itself. A single particle pair might flicker into existence. Then untold trillions of years might pass before another follows. Time, if it still holds meaning then, would stretch these events into near total isolation from one another. Certain theoretical models go further, suggesting these rare fluctuations could occasionally do more than produce a passing particle. Under precise and improbable conditions, a fluctuation might trigger inflation of its own, ballooning a pocket of space into a fresh, expanding universe. Such an event would need no prior cause beyond the ordinary uncertainty already present in the vacuum. It would begin small, unnoticed, and then grow beyond any bound. This possibility forms the foundation of a framework cosmologists call eternal inflation. In it, inflation never fully ends everywhere at once. It continues in patches, forever swelling new regions of space into existence. Our own universe, in this picture, might be one such region among countless others, expanding and cooling into stars and galaxies while inflation carries on beyond its edges. The process, if real, has no natural stopping point. Within this framework, budding is not a rare event but a continuous one. New universes may be forming this very moment, branching away from our own inflating background in a spread too vast to picture. Each new region carries its own physical constants, its own version of gravity, chemistry, and time. None of these branches could ever send us a signal or receive one from us, sealed off by distance no bridge could cross. Whether time itself keeps any meaning after heat death remains an open question among cosmologists. Once every clock, every clump of matter, and every measurable change has dispersed into uniform stillness, the very idea of before and after grows uncertain. Time may become undefined, without events to mark its passing, much like a river without banks can no longer be called a river. Others argue duration persists regardless, unwitnessed, ticking within a universe that has stopped noticing itself. Perception itself, according to information theory, depends on gradients, differences in energy that allow information to move and change. A mind, or any thinking system, needs contrast to register anything at all. Warmer here, cooler there, brighter now, dimmer before. Without such differences, there is nothing to notice, and nothing capable of noticing it. Thought, in this sense, is a process built on imbalance, never on flatness. Once those gradients disappear, consciousness as physics currently defines, it may become impossible to sustain. A heat-death universe offers no temperature difference, no available energy, and no direction for a thought to unfold within. Any mind requiring physical processes to function would lack the basic ingredients cognition depends upon. It remains an open question whether any form of awareness, however strange or unfamiliar, could exist under such uniform conditions. To witness the universe's true ending, an observer would need to endure stretches of time and cold that no known form of life could survive. Temperatures would fall to fractions of a degree above absolute zero, and useful energy would become vanishingly rare across incomprehensible spans. No shelter, no metabolism, and no material yet imagined could outlast such conditions. The act of watching may be the one thing the universe's final chapter forbids. Somewhere in a quiet room, Dust hangs motionless in a shaft of pale light, neither rising nor falling. Let your breath match that stillness, in and out, unhurried. Your shoulders can rest into the mattress now, heavy and unclaimed by any task. Each thought that drifts through your mind may simply hang there too, weightless, going nowhere, needing no answer. Rest here, in that suspended hush, and let sleep gather you inward. Long stretches of cosmic dark could still offer power, if harvested with care. Evaporating black holes emit faint radiation as they shrink, and that trickle of energy might be captured by vast structures built to encircle them. A civilization patient enough could gather this glow across eons rather than seconds, treating the black hole as both battery and furnace. Bit by bit, the whole would shrink toward nothing as its energy fed distant machines. Freeman Dyson imagined a way for minds to outlast the dying stars themselves. In the 1970s, he proposed that intelligence could survive indefinitely by slowing its own thought, stretching each mental process across longer and longer intervals of time. A mind operating at a crawl, he suggested, could match its available energy to the universe's own fading supply. Thinking less often, in his model, meant surviving far longer than thinking constantly ever could. Dyson's original calculations assumed a universe that would keep expanding at a steady, predictable rate. Decades later, the discovery of dark energy overturned that assumption entirely, revealing an expansion that accelerates rather than coasts. Cosmologists returned to his equations and found the outlook had changed. Infinite survival, once mathematically elegant, no longer held. The accelerating universe imposed limits Dyson had never needed to consider. Runaway expansion carries most of the universe's matter and energy beyond reach. As galaxies recede faster and faster, they cross a horizon beyond which nothing, not even light, can ever return. Any future civilization would find its accessible resources shrinking with each passing era, sealed off from everything expansion carries away. Total energy is not the constraint, reachable energy is. What can be touched matters more than what merely exists. A civilization anchored near a black hole might outlast one adrift in open space by an extraordinary margin. Black holes offer a slow, steady trickle of usable energy through their radiation, a resource that persists long after ordinary stars have gone dark. Open space, by contrast, empties itself of matter and light as expansion pulls everything apart. Proximity to a black hole, strange as it sounds, could become the safest neighborhood left in the cosmos. The very last usable energy in the universe may come from the slow decay of protons themselves. If protons are not perfectly stable, as some theories suggest, their eventual breakdown would release faint bursts of radiation across unimaginable stretches of time. This trickle, spread across matter that has otherwise gone dark and cold, could serve as a final, sparse source of power. Even this resource, though, would fade once every proton had completed its transformation. Certain proposals imagine black holes serving not just as power sources, but as vaults for information itself. Data encoded near the event horizon, in this idea, could persist as long as the black hole exists, protected by the very gravity that traps light. A civilization might deposit memory there, the way ancient scribes carved records into stone, trusting gravity's grip to outlast erosion, fire, and time. Retrieval would be slow, but the archive could endure for eons. Every monument humanity has built will crumble long before the stars burn out. Stone weathers, metal corrodes, and even carved inscriptions lose their edges to wind, water, and time within mere thousands of years. Measured against the trillions of years a red dwarf might shine, our entire written history amounts to a single flicker. What survives us, if anything does, will likely be far stranger than a plaque or a statue. Radio waves carrying decades of human broadcasts are already sailing outward, farther than any spacecraft could travel. Every television transmission, every radio signal ever sent, has been expanding outward as a sphere of light since the moment it left our antennas. That sphere will keep growing forever, thinner and fainter, but never entirely gone, carrying old broadcasts past stars that have yet to form. In a sense, a piece of Earth's voice will outlive Earth itself. Voyager's golden record, sealed in gold-plated copper, may drift through space long after Earth itself has been swallowed by the swelling sun. Etched with sounds and images of humanity, it was designed to withstand interstellar radiation for at least 1 billion years. Its cover carries instructions for playback, written in symbols meant to be read by any intelligence, human or otherwise. In the emptiness beyond our solar system, it may become one of the last physical traces of us to remain intact. Let your jaw loosen, as though it forgot how to hold on. Let your eyelids grow heavy, heavier than the whole day behind you. Behind closed eyes, there is only a warm, dark, wide and shapeless, asking nothing of you. Let your face settle the way still water settles, without a single ripple crossing it. Whatever thought remains can simply drift there, unfinished, and that is all right. Cosmic rays and drifting interstellar dust wear down everything they touch, given enough time. Even metal alloys designed to resist corrosion will slowly lose their shape under this constant, invisible sandpaper. Across millions of years, the bombardment is negligible. Across billions, it becomes decisive. Any object launched from Earth, however carefully built, is already being sanded smoother with every passing eon. Diamond ranks among the hardest substances ever measured on Earth, yet even diamond is not truly eternal. Over spans of trillions of years, cosmic radiation and quantum tunneling would gradually rearrange its atomic lattice into simpler forms. Carbon atoms locked in that crystal structure would migrate, one by one, given sufficient time. What feels indestructible on a human timescale is simply patient stone, not permanent stone. Even the engraved plaques bolted to Pioneer and Voyager will eventually lose their etched lines to sandblasting dust. Interstellar space is not truly empty. Fine particles moving at tremendous speed chip away at any exposed surface. Over enough millions of years, the careful drawings of a man, a woman, and our solar system's location would smooth into a blank, featureless plate. The message would still be traveling, but its message would be gone. No material yet known to physics could preserve information across the full span of cosmological time. Stone erodes, metal corrodes, and even diamond eventually rearranges itself under quantum pressure. Every method humans have devised for permanence assumes a universe far kinder than the one that will actually unfold. Anything meant to last forever must contend with forever's patience, which outlasts every design. Digital information, for all its convenience, decays remarkably fast without constant care. Hard drives lose their magnetic charge within decades, and even optical discs degrade within a few centuries at most. Every digital archive humanity has built depends on someone, somewhere, actively copying it forward, generation after generation. Without that unbroken chain of maintenance, our entire digital memory would vanish long before stone monuments even begin to crumble. A number of physicists studying nuclear stability have proposed a different approach, encoding messages inside atomic nuclei themselves. Certain configurations of protons and neutrons remain stable far longer than any material built from ordinary chemistry. Information stored at this scale would resist erosion, radiation, and even the slow decay affecting larger structures. Whether such nuclear archives could ever be written or read remains an open engineering question. Gravitational waves, Ripples in space-time itself could, in theory, carry information across distances no signal or particle could survive intact. Unlike light, which dust and gas can scatter or absorb, these ripples pass through matter almost unimpeded. A sufficiently precise message, encoded into the waveform of colliding black holes, might travel for billions of years without distortion. No civilization yet knows how to write such a message, only how to listen for one. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected the first confirmed gravitational waves, produced by two black holes spiraling into each other more than 1 billion years earlier. The signal lasted a fraction of a second, a faint chirp rising in pitch before silence returned. That tremor, stretching space by less than the width of a proton, confirmed a prediction Einstein had made a century before. It opened an entirely new way of listening to the universe's most distant events. Future gravitational wave detectors may map cosmic history back to its earliest moments. Instruments planned for space, undisturbed by Earth's tremors, could listen for ripples no ground-based observatory has ever caught. These signals might reach back before atoms existed, before light could travel freely at all. If built, they would trace the universe's shape long before the cosmic microwave background ever formed, an echo older than any image we now hold. Seconds after the Big Bang, the universe already carried a hidden signature, a stream of particles physicists call the cosmic neutrino background. Unlike the microwave glow that came hundreds of thousands of years later, this background formed almost instantly. If ever detected, it would offer a view deeper into the past than any telescope has managed. No instrument today is sensitive enough to catch it, though the ambition to try keeps growing. Notice your breath now, how it arrives, without asking permission. Let the inhale come easily, and let the exhale stretch a little longer than the one before it. Each breath out can carry a little more weight from your shoulders, your jaw, the small muscles around your eyes. Breathe in, then release it slower still, like a tide pulling back from shore. There is only this breath, and then the next, arriving on its own. Neutrinos vastly outnumber atoms in the universe today. For every atom of matter, billions of neutrinos pass through space and through your body every single second. They rarely interact with anything, slipping through entire planets as though they were empty. Despite their overwhelming abundance, this near silence with matter has made them among the hardest particles to observe directly. Residual mass in neutrinos might be enough to affect the universe's ultimate geometry. Long assumed to be weightless, they were later found to carry a small mass, though its exact value remains unmeasured. Multiplied across their enormous numbers, even a slight mass could bend how galaxies cluster and how the cosmos curves at its largest scales. Cosmologists continue refining models to account for this hidden influence. The exact nature of dark energy remains one of physics' greatest unsolved mysteries. It fills nearly every corner of space, pushing galaxies apart at an increasing rate, yet no experiment has identified what it actually is. Physics has not yet determined whether it is a property of empty space itself or something beyond current theory. Until its identity is found, dark energy remains the most influential ingredient no one can fully explain. Roughly 68% of everything in the universe takes the form of dark energy. It outweighs stars, planets, gas, and even dark matter combined. Despite dominating the cosmic balance sheet, it leaves no visible trace beyond its effect on the rate of expansion. Its presence is inferred only through the motion of galaxies, never through direct detection. Dark matter, comprising about 27% of the universe, still eludes direct detection. It neither emits nor absorbs light, revealing itself only through its gravitational pull on galaxies and clusters. Detectors buried deep underground, shielded from cosmic interference, have searched for years without a confirmed signal. its identity remains one of the longest-standing open questions in modern physics. Ordinary matter constitutes less than 5% of the universe's total content. Everything visible, stars, planets, moons, and every living thing is built from this small, remaining fraction. The atoms making up your body are, in cosmic terms, a rare exception rather than the rule. Nearly everything else in existence remains unseen, unmeasured, and known only through its gravitational fingerprints. The fate of the universe depends sensitively on dark energy's precise equation of state. A small shift in how its density changes over time could tip the cosmos toward endless expansion, gradual collapse, or a more sudden unraveling. Physicists describe this balance with a single number, one still not pinned down with certainty. Once measured precisely, it may finally reveal which ending among several possibilities the universe is moving toward. A big rip would unravel galaxies first, then stars and planets, and finally, atomic nuclei themselves. In this hypothetical ending, space stretches so violently that gravity loses its grip on everything it once held together. Galaxies drift apart long before their stars feel any strain. Then planets separate from their suns, and moons from their planets. In the final moments, even the forces binding atoms give way, leaving only scattered particles adrift in an ever-widening dark. Constant dark energy density, if that is what nature has chosen, points toward a universe that keeps expanding forever. Under this scenario, galaxies continue drifting apart at a steady, predictable rate. No sudden tearing occurs, no reversal follows. Space simply grows larger, generation after generation, without end. Cosmologists consider this the simplest, and so far best supported, version of the universe's long future. A weakening dark energy density could theoretically allow eventual recollapse. If its strength fades rather than holds steady, the outward push driving galaxies apart might one day falter. Gravity, persistent across eternity, could then reassert itself over the cosmos. Expansion would slow, halt, and reverse, drawing galaxies back toward one another. Such a fate remains speculative, resting on measurements not yet precise enough to confirm or rule it out. Feel the weight of your body now, settling deeper into what holds you. Your shoulders release into the mattress, one side and then the other. Your arms grow heavy, resting exactly where they land. Your legs sink, ankle by ankle, into the mattress beneath them. Let your head rest fully into the pillow, no longer needing to hold itself up. Everything you carry can be set down here, released ounce by ounce into the dark. Current satellite missions aim to measure dark energy's behavior more precisely. Space agencies have built new observatories dedicated to tracking billions of galaxies across cosmic history. By charting how galaxies cluster and how their light bends, researchers hope to detect any change in dark energy's strength over time. Even a tiny shift in that number could determine which of the universe's possible endings actually awaits. The Euclid Space Telescope was launched in 2023 to map dark energy's effects. Positioned far from Earth, it surveys billions of galaxies across enormous stretches of sky and time. Its instruments record subtle distortions in galaxy shapes caused by unseen mass bending their light. From this vast survey, researchers hope to trace how the universe's expansion rate has shifted across billions of years. Nancy Grace Roman, a space telescope named for NASA's first chief astronomer, will further refine cosmic expansion measurements. Scheduled to survey enormous regions of sky in extraordinary detail, it will track the positions and distances of countless galaxies. By comparing its findings with Euclid's, researchers hope to narrow down dark energy's exact behavior. Together, these missions represent humanity's most ambitious attempt yet to understand the universe's ultimate direction. Improved measurements may not fully resolve the universe's fate for decades. Even with sharper instruments, the differences between competing scenarios remain exquisitely small. Detecting them requires comparing tiny variations across billions of years of cosmic history. Careful generational effort will be required before any answer becomes clear. Cosmologists still debate whether the universe's end may ever be fully knowable. Some argue that no measurement, however precise, could ever rule out every possible future. Others hold that continued observation will eventually narrow the outcome to near certainty. The debate itself reflects how young this field remains, still mapping questions whose answers may lie centuries away. Human mathematics allows calculation of timescales far beyond any physical observation. Equations can describe a universe 10 to the 100 power years old, though no instrument could ever confirm such an age directly. Numbers extend where telescopes cannot follow, tracing possibilities across spans that dwarf the age of the cosmos itself. In this way, thought reaches further into the future than light ever could. Numbers like a googol and a googolplex appear naturally when physicists calculate the timescales of heat death. A googol is a 1 followed by 100 zeros, already larger than the count of atoms in the observable universe. A googolplex raises that number to an entirely new order of magnitude. These figures were not invented for poetry. They emerged directly from equations describing entropy's slow climb toward its ceiling. A googolplex years dwarfs nearly every physical process cosmologists have ever tried to measure. Proton decay, black hole evaporation, even the recurrence of quantum states, all complete long before such a span concludes. At this scale, ordinary units like billions or trillions lose all meaning. The number exists mostly as a boundary marker, showing where physics stops needing to count at all. A quiet comfort exists for theorists who study entropy's relentless climb. The second law describes a probability, not an iron rule, vastly likely yet not technically absolute. Every particle's motion remains, in principle, reversible under the equations that govern it. What forbids reversal is only the staggering improbability of disorder undoing itself. Rare statistical fluctuations could, in principle, reverse entropy across some small pocket of space. A handful of scattered particles might briefly organize themselves into a lower entropy state, purely by chance. Such an event would not violate any law, only defy overwhelming odds. Across spans like a googolplex years, even outcomes this improbable are not strictly forbidden, only fantastically rare. Somewhere beyond the window, a sound arrives and fades, wind moving through unseen branches, or an old house settling into its frame. It asks nothing of you, it only arrives, lingers a moment, and lets itself go. Let your breath follow that same shape, arriving, lingering, releasing. The sound outside repeats without hurry, and so can you, sinking lower with each return of its hush. Even a theoretical observer built from perfectly stable particles would still need some external source of energy to function. Thought itself requires a flow, electrons moving, gradients doing work, differences resolving into balance. In the far future, those gradients disappear as the universe settles toward uniform stillness. Without them, no arrangement of matter, however durable, could sustain anything resembling awareness. A handful of physicists have proposed that only abstract patterns of information, not physical minds, might persist to describe the universe's final state. Such patterns would need no metabolism, no energy exchange, no substrate at all. They would exist the way a mathematical theorem exists, true regardless of whether anyone is present to prove it. Whether this counts as a form of witnessing remains an open question. The very act of observation depends on some exchange of energy, or information passing between observer and observed. A photon must strike an eye, a particle must nudge a detector, something must move for anything to be known. Observation is never passive. it is always a small transaction across a gradient. Where no gradient exists, nothing can pass between one thing and another. As entropy climbs toward its theoretical ceiling, exchanges of information grow exceedingly rare across the cosmos. Particles drift so far apart that meaningful contact becomes a near impossible coincidence. Even light finds fewer and fewer things left to illuminate. The universe does not go dark all at once. It only runs out of conversations to have. Watching the universe's end may turn out to be a phrase without physical meaning if time itself loses any distinguishable structure. Without change, without gradients, without events to separate one moment from the next, there may be nothing left for time to measure. The end, in that sense, might not arrive as a single instant to witness. It might instead be the slow erasure of any moment being different from another. Certain physicists suggest the universe never truly ends, only grows fainter, its last flickers of change stretching toward, but never reaching, absolute stillness. Activity does not stop so much as thin, event by event, until the gaps between them span unimaginable stretches of time. There is no final curtain in this view, only an ever-softening hum. The universe simply continues, doing less and less forever. Cosmic time may become effectively directionless once entropy reaches its highest possible state. Without differences to measure, without gradients to mark before from after, the ordinary arrow of time may lose its meaning. Clocks require change, and change requires contrast. When contrast disappears entirely, one moment may become indistinguishable from the next. Time, in that condition, might exist mathematically without ever again describing an unfolding present. Whether the universe ends may finally be a question about what time itself actually is. Every attempt to describe a final moment relies on some notion of moments following one another. If time is fundamental, an end might be a real event, however distant. If time instead emerges from something deeper, the very idea of ending may not survive translation into that deeper language. The mystery may live in the definition rather than the answer. Some interpretations suggest the universe's ending resembles an asymptote more than an event, a line endlessly approached but never touched. Mathematically, certain curves draw nearer and nearer to a boundary without ever crossing it. Cosmologists use similar language for heat death, for maximum entropy, for the last fading light. There may be no midnight moment when it all concludes, only an unhurried approach toward a horizon that recedes as fast as it is reached. Whether anyone could ever watch the universe end depends on physics we do not yet have the equations for, on the true nature of dark energy, on whether protons decay, on whether information survives inside black holes, on rules still hidden past the edges of present-day knowledge. Tonight, the honest answer is simple. No one knows yet, and it may be a long time before anyone does. That uncertainty is not unsettling. It is roomy enough to hold centuries of careful, steady work, and it means the story of the universe remains unfinished, the way your own story tonight is unfinished too. Somewhere far off, stars are still forming. Somewhere close, your breathing has slowed, your body grown heavy against the sheets. The universe has billions of years left to figure itself out. You have only tonight left to rest. Let the vast timeline settle into the background. Let the weight of the day dissolve, and let sleep come, unhurried, the way galaxies drift toward each other across ages too long to measure. Good night.